Yes, just share my screen. Can you see my screen? Can you see the slide? Yes? Yes, I am sharing. Seems like it doesn't work. I'm sorry. Let's start again. Okay. Is that okay now? Can you see? Yes. So hello, everybody. Good evening, everyone. And good evening to our speakers to this session organized by EIROforum and entitled Bring the Future Closer. This is a purely remote session. So welcome to all of you who are listening online, and welcome to our audience in Trieste watching us live there, if there is one, for this last day of EIROforum 2020. My name is Olivier Desibourg. I'm a physicist and mathematician by training. I was during 25 years a science journalist working for media outlets like Le Temps, Le Monde, and La Recherche in France, or New Scientist in the UK. And since May 2020, I'm now the executive director of the Geneva Science and Diplomacy Anticipator, or GESDA, and I'll be the moderator of this session. GESDA is a public foundation created in Geneva by the Swiss government, the canton and city of Geneva. Our goal is to identify and anticipate the cutting-edge science advances, also technological advances, and then to try to use those advances to find solutions related to emerging challenges worldwide. We will develop those solutions not only with scientists, but also with many other communities in the vibrant ecosystem here in Geneva, in international Geneva, including, of course, the diplomats, the high-level decision makers, but also the impact people like philanthropists, and most importantly, the citizen. The overall objective is really to try to reduce the timescale between a big discovery in science or technology and its implementation for the benefit of all across the planet. So with this regard, I'm sure that this session named Bringing the Future Closer will also be extremely interesting to me, as I hope it will be to all of you. Before we start, some housekeeping information. Although I'm I'm sure that most of you are actually at home today. I will briefly introduce you to EIROforum, to the member institutions of EIROforum, and then to the speakers all together. We will have 4 presentations of 15 minutes not about each institution actually, but about chosen thematics to which many of EIROforum's institutions have chosen to give input to. And I thank there the following persons who will not speak, but are actually involved in this session. These are Claire Lee from CERN, Paul McNamara from ESA, Giuseppe Mercurio from XFEL, and Françoise Vauquois from the ILL. Before each presentation, I'll present you the speakers. We'll have no question and answer session just after each of the 4 presentations. So please keep all your questions for the end. We'll have about 1.5 hours to discuss that through the chat system. Actually, this is a purely remote session, so all the questions will have to come through the chat system of the sessions. And for those who are on site, you can either relay your questions or take the microphone to ask your questions live. So let me come now to EIROforum. Briefly, EIROforum is a network which brings institutions together, 8 actually of the continent's largest research organizations with extensive expertise in the areas of basic research, management of large international infrastructures, facilities, and programs. EIROforum combines the resources, the facilities, and expertise of all members' organizations, and this to support European science in reaching its full potential. It simplifies and facilitates also interactions with the European Commission and other organs of the EU, with governments, with the industry, with science teachers, with students, and with journalists. And for EIROforum, actually, it's more than just the sum of its parts. By combining international facilities and human resources, it exceeds the research potential of the individual organizations, achieving world-class scientific and technological excellence in many interdisciplinary fields. EIROforum works closely with the industry to foster innovation and to stimulate the transfer of technology. And finally, it operates on a rotational presidency. In the period from now, actually last month to next June, the EIROforum will be under the presidency of Institut Laue-Langevin in Grenoble. Actually, this is one of the 8 members, Institut Laue-Langevin, which you can see at the end of this list. It's the world's leading facility in neutron science and technology. You also have in EIROforum CERN, famous Center for Particle Physics based in Geneva. You have the EMBL, the European Molecular Biology Laboratory, with a center in Heidelberg, Germany, dealing with life sciences. You have the European Space Agency, which is, I think, self-explanatory. You have the European Southern Observatory, which run big telescopes in Chile, amongst others, the biggest one in construction now, the EELT, and the headquarters also in Germany near Munich. You have the European Synchrotron Radiation Facility, also in Grenoble, like the ILL, which run experiments with synchrotron light and try to look inside the matter with that electromagnetic radiation. You finally have XFEL, also in Germany, which is the world's most powerful X-ray source, and Eurofusion. It's a consortium of national fusion research institutes largely involved now in the ITER fusion reactor project in southern France. So all of them big institutions with hundreds of, if not thousands of scientists coming from all over the world. We'll now go through the presentations. I have the great pleasure to introduce you to the 4 speakers we have today, which I'm really happy to present you. And actually, we will start with Elise Vernet from the European Southern Observatory, ESO. And she will be talking about physics at the extremes with input not only from ESO scientists, but also from many other EIROforum's members to tell you about this very interesting field of research. So Elise, now the floor is yours.
Yes, 2 seconds. I'm coming, the view has changed. So now. Okay, good afternoon, everybody. So, as Olivier introduced shortly, I will present today the physics at the extreme, and I have here the contribution of 7 of the EIROforum organization. One objective of the EIROforum organization is to foster science and associated technological development. Large facility like the SFRFE, the fusion reactor of the JEC collaboration, the HLL, the X-ray free electron laser, the particle accelerator of CERN have been developed in the last 60 years to provide to the European community state-of-the-art technology, allowing to study physics phenomenon in extreme environment. In parallel, some organizational institutes like ESA and ESO have created facility to explore the extreme environment like the universe. With all this facility, researchers can explore the matter down to the atomic scale, analyze interaction with plasma, understand the chemical reaction at the femtoseconds level on the smaller scale of the physics, or at the opposite, explore the origin, the formation, and the evolution of the universe, detecting the gravitational wave, investigating the nature of the dark matter, understanding the source of the matter-antimatter symmetry of the universe, with the objective to also understand the origin of human life. So the European Synchrotron Radiation Facility was founded 30 years ago with the aim to push forward the frontier of science and technology. The extreme bright source commission is the first generation of high energy synchrotron based on a brand new accelerator design with X-ray performance multiplied by 100 in terms of brightness and coherence. To give you an example, the X-ray produced are 100 billion times brighter than the X-ray used in hospitals. This facility provides a 3D exploration of the matter down to the atomic scale. It works like a super microscope, which films the position and the motion of the atom in condensed and living matter, allowing to push forward our understanding of life at the macromolecular level, a key element for the structural biology and health sciences. It stimulates innovation by permitting improved analysis and understanding of material with the possibility to efficiently reach spatial resolution at the nanometer level. This exploration of material is an essential prerequisite for understanding the composition of the world around us, for developing new sustainable materials, innovative industrial products, and human health treatment in response to the major challenge confronting our society. It allows as well to reproduce extreme scientific environment needed for planetary science. The Eurofusion Consortium coordinates the fusion research activity in Europe. Its objective is to recreate the conditions found inside the sun as a future energy source. A successful fusion reaction requires the combining of light nuclei, the deuterium and the tritium within a plasma, a super hot form of gas. The plasma is a gas so hot that the electrons surrounding the atom have been separated, leaving the nuclei to fuse. One of the Eurofusion reactor, JET, the Joint European Torus, is currently the world's largest operating tokamak, and it holds the world's record of 16.1 megawatt plasma since 1997. There are several associated challenges. The condition within a fusion plasma must be controlled to avoid instability and disruption, causing the reaction to stop. Raising the initial gas to 150 million degrees Celsius requires multiple advanced heating systems. The Advanced Stellarator Vandelsheim 7X is the world's largest stellarator, with aim to demonstrate the suitability of the stellarator as a concept of power plant. Understanding the interaction between the plasma and the plasma-facing component will be critical for developing such a reactor. developing remote maintenance or robotic solution to perform detailed operations such as replacing plasma-facing component is critical. On JET, the robotic manipulator mascot was used to replace the entire JET first wall to test a new ITER-like wall. The Institut Langevin is a European facility providing the international scientific community with the brightest beams of neutron possible. Most of its neutron beams are used to probe materials. Indeed, due to their lack of charge, neutrons can penetrate deeply into the matter. Spain is one of the members of country of the ILL, and they are currently developing a new instrument called EXTREME-D. EXTREME-D is a new diffractometer combining high pressure and high magnetic environment associated to a high resolution, high count rate detector. With the renewed neutron guide, this instrument will open new area of research. The objective of EXTREME-D is to understand the behavior of the matter under extreme conditions like high or low temperature, high magnetic field, extreme chemical environment, to progress in condensed matter physics, solid state chemistry, and geoscience, but also in biology and health. For example, the study of ice and some other water-related systems under high pressure will allow to better understand the role of the class rate hydrates on Earth's ground, their potential role in the climate change, and their possible economic importance as source of fuel. EXTREME-D will also allow to tackle the improvement of hydrogen storage materials and the production of new phase for pharmaceutical application and to search for novel property in magnetic oxide. XFEL is the organization developing the X-ray free electron laser facility. A free electron laser generates high intensity electromagnetic radiation by accelerating electrons to relativistic speed and directing them through special magnetic structure. The laser is constructed such as the electron produce X-ray light in synchronization, resulting in high intensity X-ray pulses with the property of laser light, and at intensity much brighter than those produced by conventional synchrotron light source. High intensity laser with power larger than 100 terawatt at 10 Hertz can generate high energy plasma at high pressure and density for analysis with X-ray laser. Plasma with properties similar to the core of large planets such as Jupiter or environment similar to meteor impact can be generated. New state of matter can be observed. For example, the transition from graphite to diamond induced by a shock wave and measured by a femtosecond X-ray diffraction allow to access to the kinetics of the shock-induced transition. ESA is the European Space Agency and is pushing forward a number of spatial missions with aim to improve the knowledge of the universe and its origin, probing it using the complete range of wavelength. Amongst a number of projects currently in development, I will present 4 of them. The first one is Euclid, which is a conventional telescope of 1.2 meter diameter with 2 instruments dedicated to investigate the origin of the universe, accelerating expansion to probe the nature of dark energy, dark matter, and gravity, and also to investigate the evolution of the cosmic structure. On the other side, LISA is an interferometer with 3 spacecraft separated by 2.5 million kilometers. The objective of LISA is to detect low-frequency gravitational wave emitted, for example, by the merger of the first seed black hole, or from the merger of supermassive black hole located at the center of galaxy. LISA will also observe the cosmic evolution from the current epoch, possibly up to the time of the inflation. Athena is an X-ray telescope with objective to study the hot and energetic universe, investigating the origin of the universe, accelerating expansion, probing the nature of dark energy, dark matter, and gravity, investigating the evolution of the cosmic structure. The James Webb Space Telescope is developed jointly by NASA, ESA, and the Canadian Space Agency. The objective of this successor of Hubble is to probe the first light of the universe and the reionization, to study the formation and the evolution of galaxies, to observe births of stars, protoplanetary systems, to study extrasolar and solar planetary systems, to better understand also the origin of life. These 4 missions have been planned to observe at different wavelengths, and this implies pushing forward different technology. The LISA mission used, for example, a drag-free satellite technology, a satellite for which the payload is only affected by gravity. A test mass is placed in free-floating condition inside a shell located at the end of each interferometer arm, and it must be stable to the sub-femto gravity levels, with satellites separated by 2.5 million kilometers. To avoid noise, the entire satellite must be built as far as possible with non-magnetic material. For example, the vacuum part is in titanium. The greatest challenge for Athena is the manufacturing of the silicon pore mirror, which is made of silicon wafer shaped and with a roughness surface quality suited for X-ray application. This silicon pore optics is revolutionary for space. It greatly reduces the mirror mass and volume with a better performance. Euclid is a more conventional telescope with less technological science on the telescope itself, but with the data production processes to get the final science measurement being the critical aspect due to the type of instrument used. For the James Webb Space Telescope, there are several critical challenges, but the most critical one are certainly the deployment and the alignment of the 6.5 meter primary and the 78 centimeter secondary mirror to the nanometer levels. The European Organization for the Nuclear Research, CERN, provides to the researcher a unique range of particle accelerator facility. The Large Hadron Collider is the world's largest and the most powerful particles accelerator. It consists of a 27 kilometers rings of superconducting magnet with a number of accelerating structures to boost the energy of the particles along the way. Inside the accelerator, 2 high-energy particle beams travel at close to the speed of light before they are made to collide. As they race around the LHC, the proton acquires an energy of 6.5 tera-electron-volt concentrated at the infinitesimal scale to obtain very high concentration of energy, close to those that exist just after the Big Bang. Every 25 nanoseconds, the proton collide inside the center of the 4 large detectors, creating 2 new particles from the energy. By studying the remnant of the LHC particles collision, physicists work to answer the question, what are the fundamental pieces that make up our universe, how they fit together to form stars, planets, and indeed us. CERN has also developed the neutrino platform to foster and contribute to fundamental research in neutrino physics. The neutrino is the most volatile particle, which initially has a small mass, a trillion times smaller than the top quark. Tens of billions of them are emanating from nuclear reaction in the sun's core, pass through every square centimeter of Earth's surface each second without notice. The proto-dune detectors are filled with 700 tons of liquid argon, which need to be kept at a temperature below minus 184 degrees Celsius. When the neutrinos enter the detector, they smash into the argon nuclei and they produce charged particles. Those particles leave ion traces in the liquid, which can be seen by sophisticated tracking system able to create 3-dimensional picture of subatomic processes. Dune will not only study neutrinos, but their antimatter counterpart as well. Scientists will look for difference in behavior between neutrino and anti-neutrino, which would give us clue as to why the visible universe is dominated by matter. EISO is an international organization providing infrastructure for astronomical research. It includes several facilities in Chile, using different wavelength range measurable from ground. The major current development is the manufacturing of the extremely large telescope, which will have a 39-meter primary mirror. The ELT will be the largest optical and infrared telescope on the ground. With its first light imager and spectrograph instrument, the ELT will reach diffraction limit 8 milliarcsecond in the J-band and 14 milliarcsecond in K-band, providing images 15 times sharper than the Hubble telescope. The 1,000 square meter aperture will gather more light than all the largest optical telescope existing today. The HLT will have the capability to detect and characterize extrasolar planets in the habitable zone around our closest star, Proxima Centaurus, and beyond, resolve giant molecular clouds down to 50 parsecs in distant galaxy at redshift 2, or explore high redshift galaxy, providing us with detailed information on their stellar masses, ages, metallicity, star formation rate, and dynamical state. The telescope is using state-of-the-art technology needed to provide diffraction limit on long exposure images. The primary mirror is made of almost 800 segments actively controlled by more than 2,000 high-range actuators with nanometric precision at 35 Hz bandwidth to keep the mirror aligned while the telescope is tracking. The fifth mirror is a 2.2 by 2.7 meter lightweighted silicon carbide mirror. It's like the Herschel primary, but with, in addition, a silicon carbide chemical vapor deposition to transmit the visible light. It is mounted on the large stroke tip-tilt stage with 10 Hz bandwidth to stabilize the image movement induced by the telescope motion and wind. The quaternary mirror is a 2.4 meter adaptive mirror with 5,362 actuators and a thin mirror, thinner than 2 millimeters to control the mirror shape up to 1,000 times per second at nanometric level by correcting the residual vibration and the effect of the atmosphere turbulence. So in summary, the EIROforum institution are all working with the same objective of pushing forward the knowledge of the matter down to the atomic scale as well as on the larger scale of the universe, allowing a deeper understanding of life and its particularity and helping in improving the life on Earth with a more sustainable and reasonable manner. Thank you.
Thank you very much, Elise, for this very broad presentation. I now hand the floor to Stephanie Alexander from EMBL, and she will be talking about photon science, again with many inputs from the other members of EIROforum. Stephanie, the floor is yours.
Okay, do you hear me?
Yes.
Okay. So good evening, ladies and gentlemen. You can see my presentation, not the speaker mode. Okay. No. Okay, then I will end the show again. Hold on. Hold on. Share. Go. Okay. So good evening, ladies and gentlemen. As just introduced by Olivier, I would like to present to you what we as the EIROforum organizations are doing in context of photon science. And if I say we, I speak for Elise Vernet, whom you just heard, Isaiah Kendair from ESRF, Giuseppe Mercurio from XFEL, and myself from EMBL. What do I mean if I talk about photon science? A photon is a type of elementary particle, and in simple words, it is what electromagnetic fields consist of. It has no mass, it is not charged, but it carries energy and comes in different wavelengths and different frequencies. So for example, photons are called X-ray or X-ray photons if they are produced by electron interactions or by stimulated emission. Photons are visible by the human eye if they come at a wavelength of about 400 to 700 nanometers. Photons, as you will hear, have a very broad application in technology and research across all frequencies and wavelengths. And I can give you only a little insight today of how we apply them. What all EIROforum organizations that I present today do have in common is that we try to understand matter, or in case of our astronomy organizations, also dark matter, as we just heard, all the way from investigating, for example, chemical bonds to exploring the universe. Understanding matter has always driven human progress, and synchrotrons, which are producing X-rays, are, as you heard, are more and more used to understand the complexity of matter at all scales. Today, the synchrotron community represents around 50,000 users worldwide with around 50 facilities. The EIRS-RF is the most intense synchrotron. As you heard, it just opened a new generation of high-energy synchrotron after a major upgrade funded by 22 partner countries. It is open to the scientific community of the entire world and contributes to tackling global challenges in many, many key areas. Those include health, like investigating the structure of viruses, the environmental challenges, energy challenges, and new industrial materials, but also, and this might not be known, to unravel hidden secrets of our natural and cultural heritage through the non-destructive investigation of precious artifacts and paleontological treasures. X-rays generated by a laser are used at the European X-ray free electron laser facility. And XFEL is the first user facility that generates both soft and hard X-ray FEL pulses at the megahertz repetition rate. As you already heard, in contrast to a synchrotron, the UXFEL generates ultra-short pulses of 2 to 100 femtoseconds with a very high photon density, 10 to 13 photons per pulse. And this creates a huge energy, up to a few millijoule, and a high transverse coherence. These properties are used on the one hand to investigate ultra-fast dynamics of liquids and solid matter with high spatial and temporal resolution to better understand chemical reactions. For example, how to convert solar energy into electrical power, or how to develop new materials for new memory devices to cope with the big data challenge. Imaging can also be done at the nanoscale of biological samples, which helps, of course, the development, for example, of new medicines. And also, nonlinear X-ray science triggered by the large intensities reveals new phenomena in atoms, molecules, and solids. So the next slide will give you two specific examples. So free electron lasers can be used to study the chemical reactions taking place at solid surfaces to gain a fundamental understanding of the formation and breaking of molecular bonds, and use this knowledge to develop more efficient catalysts that help to remove toxic agents, for example, from car exhaust. XFEL can also contribute to the development of the next generation of magnetic memory devices. For example, a skyrmion, that is a topological magnetic structure, can represent a bit of information. Skyrmions can be generated on a magnetic multilayer only by absorption of optical light. And understanding how these structures are generated and annihilated is essential to develop this technology. At the European Molecular Biology Laboratory, we are using photons and electrons, I have to admit, in imaging technologies to unravel life across scales and in context. You must understand that the structure of a biomolecule does change dependent on molecular interactions, and interactions change in context of a cell. Again, cellular function does change in context of an organism. And as we have so many different cell types in our body, this is very important to understand. Again, organisms behave then differently in different environments and ecosystems. So crossing scales is important to understand the development of life and disease. At EMBL, researchers have the benefit that they can apply the latest imaging technologies developed by the physicists and engineers in-house to accelerate their research. What I would like to show you here is the first virtual embryo. So despite advances in the field, a complete representation of embryonic development, accounting for every single cell in space and time, has not been achieved until now. So EMBL researchers were able to solve this problem by constructing a virtual embryo of Felusia marmellata, which is a marine tunicate known as sea squirt, which is found in the Mediterranean Sea, but also in the Atlantic Ocean. And this species was picked as a model or system because it is related to vertebrates, believe it or not, because it recapitulates the embryonic cell diversity of a vertebrate and has a very stereotypic cell division. To generate this virtual embryo, we combined high-resolution single-cell transcriptomics with light sheet imaging. And light sheet imaging is a very mild imaging approach using photons of the visible light that does not harm living cells, and it does not disturb their developments because the photon density is so low. So combined, those data map single-cell gene expression profiles onto spatial organization in the developing embryo. We capture here every single cell at every cell division up to the 64-cell stage, when all cell lineages, meaning all cell fates, are determined. So it is defined which cell will become in the future part of the nerve cord, part of the brain, a germ cell, a blood precursor, and so on. So this virtual embryo will help to answer how the different cell types in an organism can originate from one single egg cell. But as you might know, in reality, access to such imaging technologies is limited. A small university cannot afford expensive microscopes nor the experts to run them or analyze the data. So in addition to its own research, EMBL has the mission to provide service to the scientific community and does this by providing access to state-of-the-art facilities run by leading experts. We do structural biology services at our Hamburg and Grenoble sites that cover the whole process from sample to structure, meaning this includes access to beamlines in collaboration with other EIROs, such as ESRF or ILL, as well as high throughput sample preparation, cryo-electron microscopy services, and data analysis support. In addition, EMBL is currently constructing a brand new user facility, an imaging facility at its Heidelberg campus, the EMBL Imaging Center, which will hopefully open in summer next year. The EMBL IC will provide access to the latest imaging technologies, including those developed at EMBL and being not yet commercially available. The technologies will range from cryo-electron microscopy all the way to light microscopy of different resolution. We will provide access to super resolution technologies such as single molecule localization and stimulated emission depletion microscopy that can image below the diffraction limit of light, and by this bridge nicely to the structural biology methods. We will offer service on light sheet microscope at different scales, from super resolution to whole organism imaging, as well as to the latest and advanced multiphoton microscopes for deep tissue imaging and large organism imaging. The service that we are providing on those microscopes will have, in addition, a special focus on correlating, meaning combining all those technologies to enable the user in the long run to, for example, unravel the structure of a certain protein of interest inside a particular cell type of the organism of interest on which we just had done live imaging beforehand. So how does correlative imaging looks like? So I took a recent example, and you see here the worm C. elegans. This worm lives in soil and it's a very popular model organism for neuronal research and research around development of the brain and the nerve system. So we did live cell imaging and observed its development. And then we froze it down in a block of ice. And again, we use light imaging, confocal imaging, to find our worms back in this block of ice by labeling a centrosome marker. And with this, we can also zoom into the gut region of this worm where this marker is expressed. And then we can exactly define the position, so do targeted lamellae position. And this lamellae, we can then cut out by ion beams and transfer the small lamellae into a cryo-electron microscope to do cryo-electron tomography and unravel for example, the structure of ribosomal subunits. Although not shown here in this resolution, we can now achieve resolution below 10 angstrom, meaning below 1 nanometer, and that from proteins inside cells and organisms. In the EMBL Imaging Center, we will also provide tailored project support, meaning, so we start with a sample preparation and we will advise on this. Then we go via the imaging at the microscope itself, all the way to data analysis. We will also implement many training opportunities for our users, but especially also for research staff from other facilities across Europe, to be able to spread the knowledge and again increase the capacity for service. And also we want to work closely with corporate collaboration partners in open innovation format. And the first contracts have been signed here to allow effective commercialization of the newly developed imaging technologies and workflows. Last but not least, I would like to introduce how photons of the visible light spectrum are used in astronomy to unravel the secrets of the universe. So at the European Southern Observatory, for example, lasers are used to create so-called guide stars. Here, a laser beam is focused in our atmosphere at about 90 kilometers altitude, where a layer of sodium atoms is present. And these atoms are excited by the laser light. Of course, this needs a particular wavelength. And then they emit photons, creating an artificial star. Those artificial stars are needed to correct in real time the image of the astronomical objects using adaptive optics. The image that you can see here is actually showing the device, the machine, however you want to call it, creating the guide star with 4 laser beams at the Very Large Telescope in Chile. There is now the first telescope fully dedicated to astronomy with adaptive optics and laser guide stars. And this makes it possible to improve the images substantially. So you can see down here an image of Neptune with the correction by adaptive optics and without. The second application I would like to show you today is the laser comp system. Here, a laser and a fiber scrambler, you see those here, are used to provide a spectrum with very sharp emission lines, which have a wavelength that is very stable over a long time, so for years. And this emission pattern is superimposed on the spectra taken of stars and possibly reflected light by planets. So from a spectrum, the distance of a star can immediately be found by the Doppler effect. So when measuring the same spectra over time, let's say on different days, one can check whether the position of the spectrum is slightly changing with respect to the calibrated emission line pattern, and in that case, precisely measure the radial velocity of the stars, deducing the presence of planets. With those very exciting examples, I would like to end my presentation, and I hope that I could give you a little bit insight into what we EIROs do in photon science and how we are serving the scientific community and science in general. Thank you for your attention.
Thank you very much, Stephanie, for this very luminous, if I can say, photon science presentation. Okay, thank you very much for the information. Now the floor is to Gregory Keach for EUROfusion. He will be talking about energy for the future.
Oliver, can you hear me okay?
Okay, now Greg is on. Thank you.
I have to keep my camera off due to bandwidth, but thank you. So this session is about energy for the future. My name's Greg Keach. I'm an engineer at the Atomic Energy Authority in the UK, which is part of the EUROfusion consortium. So I thought we'd all be familiar with the negative impacts of burning fossil fuels. So climate change, rising sea levels, a lack of fuel security, and also localized pollution. The graph on the right, oops, sorry, let's get one side back. The graph on the right shows the energy distribution. far right of the graph, we would only see a rise of 2 degrees. But of course, this would require a huge increase in renewable usage, up to 65% of the overall production, and 29% of that being from intermittent renewable supply. I think what's interesting about this graph, though, is it actually shows there's no one clear solution for future energy usage. In fact, we're going to need lots of solutions from different sectors and different parts of the energy generation and supply, and also effective usage. So there's different intelligent ways we can produce energy. There's different intelligent ways we can transmit and also store energy. And there's also different ways that we can use energy more intelligently. Of course, within that, we've got tidal, different uses of atomic energy, wind energy, but also different ways that we can store it, and also how we can use it in a smart way. And again, across this board, we have to come up with different solutions, and across Europe work together to tackle what is going to be a global problem, as we don't just see a rise in population, but also a rise in the amount of energy that people within that population will be using around the world. So a nice example that's coming from CERN. So at CERN, the European Organization for Nuclear Research, frontier research into the fundamental particles that make up the universe has required more and more powerful accelerators and more complex detectors over the years. And so CERN uses 1.3 terawatt-hours of electricity annually, with a peak consumption of about 200 megawatts between May to December, while the LHC complex is running about 1/3 of the energy required by Geneva. In the future, one of the hopes is to build a much higher energy collider, and the power requirements will increase accordingly. CERN is currently researching new technologies, such as the use of superconducting wires that can conduct up to 100 times the current of traditional copper wires, and reduces the problem of energy loss during transport. So in the image, we can see the copper wire on the left is 11 centimeters high, 8 centimeters wide, and 28 centimeters long. It can conduct a current of 12,500 amps at room temperature, but when cooled to 1.9 Kelvin, the niobium titanium coil on the right enters a superconductive state and conducts the same current despite being a much smaller size. So I think this is a nice example of how research being done at CERN to improve their own efficiency, we could actually see in the future being brought into the energy distribution sector. So in the same way at ESRF, one example of research being carried out there is the study on batteries. So indeed, one of the great challenges of the century is to store and distribute effectively clean energy, and in the case of batteries, to understand and to improve the function of batteries. So with the third generation source, ESRF, made first attempts in following the fate of lithium atoms during charging and discharging cycles. So during charging and discharging, several phases of lithiated graphite appear. There is still some debate about the mechanisms and some phases, but it's accepted that the fully lithiated phase is known as LIC6, it's called stage 1. Other phases are stage 2 and stage 2L. Between stage 2L and pure graphite, there are many phases, not easily to distinguish for us because we do not have sufficient resolution. All what is beyond stage 2L is defined as stage 3. The lithium content of stage 3 is attained from peak position, so peak position in linear with the lithium concentration from stage 3. So we see in the graph, the yellow is the amount of lithium from stage 1, the orange is the amount of lithium from stage 2, and the red is the amount of lithium from stage 3. With the new cyclotron open on the 25th of August 2020, the ESRF will allow scientists to see the atomic structure, evolution at extremely fast charging and discharging rates, and be able to enable direct connection with sample processing and an AI-driven smart design. So moving now towards not storing or transporting power, but actually producing energy. So the Eurofusion mission is driven by the need for large-scale, sustainable and predictable low-carbon electricity generation in a likely future environment where the global electricity demand is greatly increased. A predictable baseload supply is needed to handle short-term and seasonal variations in the renewable sources, such as wind and solar. So the approach is to take the process that powers the sun, nuclear fusion, and we can find a fusion plasma. So we take a hydrogen gas, we take it up to about 10 times the temperature of the sun, 150 million degrees, And we combine that using a set of very large electrode magnets. And the process there is we then capture the high-speed neutrons, and we use that to generate energy. So where is our actual roadmap going? So currently in the short term, we're supporting the construction of ITER, and that's research and development in support of their mission. They recently passed a really exciting construction milestone. I believe it's now 70% complete in its assembly. But continued deuterium and tritium operation in JET. So deuterium and tritium are isotopes of hydrogen, and using deuterium and tritium, we hope to have higher energy plasmas that are much more suitable for a fusion power plant. We're also in the research and development and concept design stage for demo, and also supporting that, we need to look at the materials that we're used in such a reactor. So the construction of testing facilities, IFMIF and DONES. In the medium term, we hope to see much more scientific and technical exploration of ITER as it begins to operate, and also our test facilities, IFMIF and DONES as well. And then we can start to begin the engineering design phase of demo with industrial involvement too. But to do that, we need to still increase the supporting research in power plant materials and technologies. And as well with Wendelstein 7X, we hope to understand from the standard rotor concept how that can start to influence the design of demo. In the long term, we hope to see high performance and high power performance of advanced technologies in ITER, and we can use that to qualify long life materials for demo and power plants using IFMIF and DONES as well. And finally, moving into the finalization of the demo design and beginning the construction of demo, which will be a first of a kind fusion power plant or near fusion power plant. What we start to see though is from JET, so it's a 3,000 ton device. I'm afraid the picture might be a little bit small to actually be able to see the to see a ladder in there to get an idea of scale. But we're getting bigger and bigger, so ITER is an even bigger device. And finally, to this artist's impression of demo. The reason that we have to keep getting bigger is obviously the sun is very large itself, so very high density. It's also very high temperature, but it has a really large confinement time. So that's the amount of time it takes for an energized particle to leave the reaction. Now, of course, on Earth, we can take those temperatures up to 10 times the temperature inside the sun, but we become a bit unstuck with density and confinement time. So we have to get bigger and bigger plasmas to actually get up to the plasma volume where we can have a more power plant-like reaction. So what we start to see is JET has about 80 meters cubed of a plasma volume. So this is a cross-section looking inside the plasma, and the plasma being a torus or a donut shape. ITER is going to be even bigger, up to 800 meters cubed. But for a successful power plant demo, we're going to need about 2,200 meters cubed. So the reactors get bigger and bigger. And of course, this drives a lot of physics and engineering challenges. So if we actually start to look at what is demo, so the central requirements for demo lie in its capability to generate between about 300 to 500 megawatts of net electricity to the grid and operate what we call a closed fuel cycle, meaning our spent tritium fuel will be reprocessed and reused. So the current fusion experiments that Eurofusion do primarily investigate plasma physics. However, demo must demonstrate the necessary technologies, not only for controlling more powerful plasmas, but also safely generating electricity. So that means regular, rapid, reliable maintenance of the plant, and the design of such plant must take into account not just the physics requirements, but also engineering and technology limitations. So the picture on the left, if we were to take the demo concept reactor and we were to cut it into 16 slices like a cake, this would be one of those slices. And so this is about 15 meters high. So in the middle of the chamber is where we would suspend the plasma. And we suspend that plasma using these very large electromagnets, superconducting electromagnets. And we also control the position of that plasma using these poloidal magnets around the outside. We need a vacuum vessel because we have to evacuate any gas that would disturb the plasma and would take energy out of it. Around the outside, or within the vessel, around the outside of the plasma, we have what are called breeding blankets. So these are really crucial in moving from a fusion experiment to a fusion power plant. So these do two functions. They obviously get hot through neutron bombardment, and we use a heat exchanger to cool those down, and then turn that to steam to turn the steam turbine. But if we actually fill those with lithium, the interaction of neutrons with lithium produces tritium. So our two main fusion fuels are deuterium, which is an isotope of hydrogen, and about 1 in 6,000 isotopes of hydrogen in seawater are deuterium. So we've got about a few million years worth of deuterium fuel in the oceans. And tritium we can breed from the reaction itself. So by doing this, we actually have a very closed fuel cycle where the tritium fuel that we'd use, we can also breed from the breeder blankets. Of course, there's much more challenges to fusion as well, such as how do we exhaust the helium that comes out of the plasma, the small amount of helium. So to do that, we need materials that can interface with the plasma. At this stage, it's not 150 million degrees, but it's still a super hot gas. And so a lot of material research needs to happen as well. I said before, one of the key things about demo is it's not so much a fusion experiment, but a power plant-like device. And what's really critical here is reliability, availability, and maintainability. So how often, or not how often the machine breaks down, but obviously the machine has to be super available, and we need to have certainty that the machine is not going to stop. So that's really critical, and a large area of research is actually looking into how do we maintain the machine. I think fusion is very interesting because across fusion, we have just more than plasma research. I've already mentioned materials, but we also have a lot of robotics and also maintenance technologies. For example, removing these breeder blankets from within inside this magnetic cage that we have and inside the vacuum vessel has required advanced robotic research. So we're looking at moving almost flexible blankets that will deform about 10 millimeters when we lift them. They weigh about 80 ton and they're about 10 meters high, through really challenging kinematic paths. And so to do this, we're actually developing unique control systems that can react using artificial intelligence to the movement of the blankets as they're lifted. So I'd just like to conclude by going back to this point and really asking the question that I think we could take forward to the discussion maybe, about how do we approach the challenge of providing the world with clean energy, clean, sustainable energy for the future. And I think the answer to this will be cohesion. We need to link the power distribution with the power generation and also the usage and all the different disciplines, fields and areas that can contribute to that. Again, I don't think there's one silver bullet for this. There is no one single solution, but it's going to rely on a lot of collaboration and a lot of great novel ideas as we move forward in the century. So finally, thank you to the contributors from ESRF and also CERN Fermilab, and thank you for everybody's attention.
Well, thank you very much, Greg, for this nice presentation. Our last speaker today is Isaac Candia from ESRF in Grenoble. And again, we're leaving the field of physics to enter back the field of life sciences, as she will be talking about drug and vaccine discovery and development. So Isai, floor is yours now.
Thanks, Olivier. Hello, everyone. Thanks for being here amidst all these very difficult, tough times. Thanks to decades of research has been done in this field, now we are living longer. Yet, we all know that there are lots of chronic diseases. Right now, we are going through one. And apart from these infectious diseases, we also have heart-related diseases, cancer, and a whole load of other diseases for which, for the moment, we have the potential solutions we have are the drug and vaccines. So today I'm going to present what are the contributions from all the EIROforum institutes towards the discovery and development of drug and vaccine. First, I would like to just start with a small example, which I have shown here is called opium. Everybody knows about this, I presume. This is the most used analgesic at the moment. Now, opium, this fight against pain is not something new. It's been documented since 300 BC that opium has been used to relieve pain. Now, what we have right now, the morphine or different derivatives of opium are all possible only because there were lots of fundamental researchers that went behind these findings. Now, just to name a few, the first discovery, how to crystallize this compound from the latex seeds or the latex of the opium seeds. And the second a notable discovery is the crystal structure or the chemical structure of this compound. And finally, only in 2015, there were very useful insights of how this compound binds to one of the most popular receptors, which are called the GPCR receptors, a Nobel-winning topic, to say how these molecules bind to this compound. Now, all these fundamental researches were crucial to what we have right now, the most used compound, namely the morphine. So just to say that now, if you see the morphine market, you can, I don't need to explain this in words, so you can see that it contributes to the global market revenue as a substantial value. And all this has been possible because there were lots of fundamental research that went through all these technological advances, which produce all these innovations that help man's life. Now, the fundamental research is the major goal of all the EIROforum institutes. Due to the time limitation, I couldn't present all the institutes of the EIROforum which have contributed to drug and vaccine development, but I will present only 4 institutes here, namely XFEL and EMBL and ILL and ESRF. So the first one is about the development, the contribution to the drug development from XFEL. XFEL, you all know that this is the longest light source. It's about 3.4 kilometers long, and it produces the extremely intense X-ray flashes. Now, researchers use these X-ray flashes to do lots of studies, mainly to do the atomic details of viruses, to film chemical reactions, and even to study processes in the interior of the planet. Now, these are so intense pulses that they distract the object immediately, but just giving enough time for the object to diffract. Now, this is a very special property of this XFEL rays, and it has a popular name known as diffraction before distraction. And now this technique, using this process called megahertz serial femtosecond crystallography, which has been used by European XFEL researchers to develop drugs against several diseases, including Alzheimer's. Now, this technique also provides lots of molecular movies about, at real time, and then they can use these movies to understand the enzymatic reactions, which are used to make the existing drugs more efficient with less side effects. Also, these high intensity X-rays are used to map the weaknesses in virus or bacterial outer coats, and thereby they can understand or develop drugs against these microbes. And one of the most notable contribution to health challenge from European XFEL is a study of the microbial antibiotic resistance. And this is currently, WHO has rated this as one of the biggest health challenges. So now EMBL, as you all know, is the flagship research institute for life sciences in Europe. And the researchers, they employ several modes of action to combat numerous diseases. Now, either they use a specific target, such as the influenza virus polymerase, to develop antiviral drugs against this virus, or a more systematic approach where to identify drug targets in living animals, thereby to have a global view of all the drug targets and therefore the potential side effects. EMBL researchers at EBI, they are involved in collecting, storing, and sharing data, and it's a very large-scale project. And to give some examples, it's the Protein Data Bank, which contains more than 150,000 protein structures, which are completely used in drug discovery. And the Pan-Cancer Project also, which collects and analyzes more than 2,600 cancer genomes from 38 cancer types. Now, examining all these genome patterns will help, or it could help to tailor a cancer-specific treatment or for a specific patient. Also, EMBL is involved in technology development, which assists in the development of new drugs. One example is AlpX, which is a newly formed spin-off company from EMBL Grenoble. Now, AlpX has created a fully automated and remote-controlled protein to structure pipeline for protein crystallography. And now this new technology greatly reduces the cost and time taken for drug research. Now, in relevant to the present day pandemic, I would like to present some of the contributions that EMBL has presented. For example, EMBL has launched more than 20 research and support projects contributing, combating the SARS-CoV-2. Now, EMBL also made facilities in Heidelberg, Hamburg, and Grenoble available for coronavirus-related projects. Also, staff at EMBL EBI and collaborators, they created the COVID-19 data portal, which enables the sharing and analysis of all the coronavirus-related data. Now, this aims to facilitate the international collaboration to accelerate scientific discovery, monitor the pandemic, and help develop treatments and vaccine for the virus. Now, scientists at EMBL Heidelberg have created a database of more than 4,000 RNA binding proteins called RBP base, which helps researchers to identify cellular proteins that interact with SARS-CoV-2 RNA genome. Now, EMBL Grenoble and EMBL EBI are carrying out research to identify and test existing drugs that have shown potential against SARS-CoV-2, with 7 promising candidates already identified. Now, scientists also working to identify neutralizing antibodies that could stop SARS-CoV-2 before it enters the human cells. Now, scientists at EMBL Rome, they have used epigenetic modifications to stop expression of the cellular protein that SARS-CoV-2 uses to infect cells. Now, coming to Grenoble, we all heard about ILL already. So this institute uses neutrons. And as we all know, neutrons is a key component of the atomic nucleus. So lately it is also used in health sciences to combat diseases. The major, some of the examples to say is in nuclear medicine, which is the boron neutron capture therapy, which has been used to specifically kill unhealthy cells. In a similar manner, radioisotopes have been developed to target only cancer cells. Also, neutrons are exploited to study the structures of viral proteins that are crucial for its reproduction and thereby develop antiviral drugs using a technique called neutron crystallography. Now, ILL researchers also use this technology, neutron crystallography, to design drugs to tackle several diseases. One example I have shown here is to counteract amyloidosis in heart. So there is this protein which is named transthyretin, which is a normal hormone transporter. And normally it functions fine, but under circumstances, it can go haywire and form amyloids. And this creates a major disease, namely a fatal cardiomyopathy and polyneuropathy. And the only solution is to do a heart transplant, but we all know how intense it is. So now drugs are being designed and characterized to stabilize this particular transthyretin molecule so that its misfolding can be prevented. So to talk about ESRF, my name is, I didn't say clearly, but my name is Isai Kandia. So I'm representing ESRF and I'm working as a structural biologist in this institute. And as you all know, ESRF is an international facility pioneered in synchrotron sciences. And it is funded by 22 partner countries united by the same aim to push forward the frontiers of science and technology. Although the major topic is physics, many ESRF beamlines are even involved in tackling several health challenges head-on. Now in ESRF, research enhancing the know-hows of increasing biological complexity and integrity in increasing resolution is currently pursued. Two sets of beamlines are dedicated towards this. One is the structural biology beamlines and the other one is bioimaging beamlines. Now for structural biology, there are 8 dedicated instruments for, to help the researchers from its member countries and also all over the world to understand, for example, how antibiotic resistance is developed in microbes, to develop drugs against several bacteria, and as well I have listed some of the viruses here, to develop vaccines and antiviral drug developments for various viruses. Many of these results have been deposited. More than 600 structures have been deposited, leading to 150 plus high impact publications. Currently, the user community is big with 1,800 users in structural biology. So again, related to the current pandemic, I would like to present few things which ESRF has contributed or is currently pursuing as well, is to attack COVID-19 in 2 perspectives. So the first perspective is from the viruses to identify viral proteins for potential drug targets, employing structural biology techniques to study the structures of these proteins and then use these structures to develop lead compounds using fragment screening. Now, from the host perspective, we have used the bioimaging beamlines to understand the lungs microstructure and how infected COVID-19 patient lungs looks like compared to a normal lungs. And this enhances the impact of the virus on human organs. And this would also help to develop drugs to alleviate all these impacts. With this beam, already it has been mentioned several times during all the talks that ESRF has gone through the major upgrade recently. So in 1988, ESRF was the first 3rd generation synchrotron. And now this year, it has been opened as the first high energy 4th generation synchrotron. Now with this upgrade, which we call ESRF EBS, several of the beamlines will be upgraded and the applications from these beamlines will be skyrocketing. But I would like to just share one of the most exciting application in relation to this topic, namely the bioimaging beamlines. So as I said, as I mentioned before, they can see the lung tissues up to 2 micron resolution. Now with that, and with the other beamlines, which can currently can scan larger objects. Now combining these two, one can expect, or we are planning to do a large-scale super medical scanner, which is very useful for research and virtual histology. So we are all really excited about this development, and really the medical community is highly excited. So just to finish, all the contributions. So I couldn't present all the contributions, as I said, but I hope I convinced that European research infrastructures, all the institutes have contributed a decisive role towards the drug and vaccine development. There are much more to be done in this field and relevant to the present pandemic and for all the emerging pandemics. We should be prepared much before and we should combat with a much stronger and combined effort is required towards that among the private and the public sectors. So with this, I will finish and thank you all.
Well, thank you very much to all of you, to the 4 of you, for those very interesting and rich presentations. Again, I will ask the audience, the online audience, to don't dare ask their questions through the chat. The chat system is working, so please do send your questions that I will relay to the 4 speakers that we have today. Well, we talked about extreme physics. We talked about virtual embryo. That was fascinating, actually. We talked about nuclear fusion, which is a really huge and fascinating project as well, and even about opium and many different things as well. So a very diverse set of presentations, I would say. And I'm, of course, very happy to take any questions, specific questions about the 4 presentations, if there are some. But I'd also like to bring the discussion to another level, maybe at the level of EIROforum, and to take all of us a step higher and try to have a broader or more common view on all your research fields. And actually, if we think back of what we said at the beginning, saying that EIROforum is more than just the part of the sum of its parts, I would like to know if you can give us very concrete examples of maybe how you work together, how you concretely work together to, well, to bring this future closer, as the title of the session goes. And maybe, especially now in those very strange and exceptional times. So how do you concretely work together as scientists? Who wants to take the floor? Isa, you had very interesting insights when we prepared the session.
So I can talk for the COVID, during the COVID pandemic, which is, I think, more relevant and more interesting, perhaps. So during the pandemic, all the EIROforum institutes meet quickly, and several decisions, very important and useful decisions, have been made. And several of the facilities have been open for COVID-19 projects to help all the researchers worldwide. And I think this is very important because I mean, it's a very tough time for everyone. So opening the facilities is a very good thing. And also I mean, there are several other examples to say how we work together, but yeah, this is one example. I would say that it was very important during this time.
But is there maybe a project that you were asked to collaborate to, involving many different of the members' institutions? Stephanie? Or,
yeah, so maybe I can jump in with a very specific collaboration that we had now during COVID. So ESRF and EMBL founded the so-called Joint Structural Biology Group. And this was a collaboration basically between the high throughput crystallization lab in Grenoble, as well as also the sample preparation and characterization facility in Embel, Hamburg. And then jointly with ESRF's beamlines, so that users working or scientists working on COVID project basically had to write only one project proposal. And then you had access to all of the facilities instead of applying to each individually. And that, of course, accelerated the use and the structural biology in those regards.
Yes. Yeah,
in preparing this talk, we also mentioned the vast computing power that had to be put at disposal. So we have no representative from CERN, but maybe someone else would like to react on this.
Yeah, I can, for example, speak for the COVID data platform that Isaiah also mentioned during her talk. And that was basically a collaboration between EMBL, EBI, the European Commission, the European Open Science Cloud, and several other partner institutions all across Europe. And simply to collect all the data in one spot and provide the computing power and simply the storage power that researchers from across the world could access it. And really during the first 4 months, there were 73,000 users from, I don't know, over 180 geographical localizations who access data, and simply to merge and in power and computing power. So yeah, and CERN did support us in computing power wherever need was, and yeah, so that is one example of where we work together in terms of data.
I'd like to give the floor to maybe Greg and Elise if they have something to say before coming back to you. Isai?
Yes.
Greg, yeah?
Yeah, sure. The particular example that comes to mind, but I think what's been interesting for this session is seeing a lot of parallels in what I would call enabling technologies. So we've seen, particularly looking at what CERN are doing and also with the space agencies, the scale of the equipment, but also the tolerances that people are working to as well. So there's loads of parallels there. And then when we look at specific technologies like superconductors. So and I think that's really interesting how there's a lot of similar problems that everybody's working on. So I think forums like this are great for sharing that innovation and how people are working on those problems.
Isai?
Yeah, just to say that apart from this pandemic time, there has been collaborations between all the institutes for a very long time. One local example I can tell is this partnership, the structural biology, that combines all, not only the European institutes, also with the 2 French institutes. I mean, with 1 French institute and 3 European institutes. This is a very strong structural biology collaborations. And apart from that, perhaps everybody knows this ATTRACT. There are several other projects that have been formulated among the institutes to not only to develop just research, but also to close the gap between the public and the private sectors. So the example that I gave is this ATTRACT project. And I mean, these are the things that comes up in the mind now.
Actually, that was one of my follow-up questions. Do you see ways to improve that international collaboration or inter-institutional collaboration? Are there ways to really, get you more together than you might be already?
So maybe I can comment on this.
Yes.
We have tried both between ESO and ESA to collaborate on the technology development, because this is always a high cost. So, for example, ESA is also interested now in adaptive optics, and we are working together to define a common requirement and to then run development with industry to manufacture these deformable mirrors. So there are a lot of collaboration on this. We have also collaborated with CERN more in the framework of designing. For the new facility at CERN had the need to have some mirror optimized with their mount, and ESO proposed it helps, and we provided the analysis required for CERN. So I think it's important to define specific project, and find, I would say, the excellence of each institute and try to help the other which do not have this excellence.
Does someone else wants to take the floor on this? Otherwise, I'd like to bring you to another level now also. If we take back the title of the session, namely Bringing the Future Closer, it's talking about the future. But we see it, Greg, I'm watching you, with nuclear fusion, it's a long way. It's still a long way. You're making great progress. ITER is being built now in Cadarache, etc. But I wonder, especially now in those very strange times, how maybe difficult or strange or easy maybe it is to still bring this message around the fascination, the interest of science, of the necessity of the big science, long-term science, fundamental science, and also the science at the extremes as we saw. How is it easy or not to really maintain this fascination? I'm also thinking about the governments, because the future is the future, and governments tend to sometimes see it a shorter view. So how is it now in those strange times to maintain this fascination for the science that you're doing?
I think
Greg and then Stephanie. Yep.
It's always good to think about these challenges as things that are urgent and things that are important. And in these strange times we're seeing currently with the pandemic, that's something that's urgent and important. But I think particularly when we talk about the future of energy and the future of big science, that is something that might not seem urgent, but is very important. And so we can't forget that. And I think that the way we do that, the way we keep moving forward, is to remind people of that as well. I like to think with fusion, it's just a very exciting field anyway. We have a very clear mission. and a very exciting one as well. And ultimately, the devices that we're building are trying to take those conditions inside the sun. We are literally making mini stars on Earth for a future sustainable energy source. But yeah, I think it's keeping that communication about all the interesting work that's being done, and also highlighting, particularly in fusion, how it's benefiting other technologies, materials development, maintenance and robotics, just to name a few, magnets as well. Sort of showing as well how we're outputting spin-offs and furthering those fields, as well as achieving that main goal.
Stephanie, you wanted to say something?
Yeah, I think in general, it was, maybe that's not the most intelligent way to say it, but I think it was a very good time and still is a good time for science, because now suddenly the news are dominated through science news or scientific news. So suddenly, even be it physicians or be it fundamental researchers, but in general, suddenly science is cool because it's really driving progress, and other components like classical politics, religions. Of course, they have still their position in the news, but now also science is there, and independent of the science we are doing and what we are trying to drive forward, suddenly there is an interest of the public in science again and how relevant it can be. And, you know, then always a crisis helps to suddenly wake people up again. And this can be a catastrophe in terms of environment, but it can be also a pandemic. And I think as long as science, this interest is there, again, it helps all of us.
What about you, Elise? What about astronomy? Does it take its part in this pandemic as well? Is it following the big move as that Stephanie is describing?
Yeah, I think people are, I don't know if we can say that it's linked to the pandemic. I think that people are always interested to know from where they come from, how we have been built, and this is not changing even if we have the pandemic. Maybe they come back to the origin and they want to know more. I would say that it's not stopping. So they are still interested, and they are still seeking to have information on this fantastic universe we have around.
But still, they would prefer to have a vaccine or a treatment, or the real clues on how to fight the virus now. Maybe rather than knowing that two black holes just collided or so.
I can understand your point. I agree, but it's not the same frame. I would say the same time. The vaccine we hope will come soon. The black hole are long time research, and it will not change. I think anyway, science is also, as we have always all said, it's important also to seek to continue to follow science, because all these big buildings we are doing are done by industry. And if suddenly we stop giving money to the science, industry will just disappear. You know, at ESO, we have now REOSC, who is the French company building all this 1,000 segment for the primary. If we tell them to stop, they have just finished, they have just started to build the first and they have a complete company just for this in Poitiers, and it would mean that this company would disappear. So I think we cannot stop from this.
Yeah. Shortly, Isai and then Greg, because we are running out of time. So Isai first and then Greg.
Yeah, so just to say that as Stephanie was saying, the science, the interest in science is the major driving force here. And right now we have the pandemic, but the studies in astronomy or physics or in synchrotron science or in the energy or everything is going to help at some point. I mean, as I was saying, that right now we have some innovations, but there is like centuries of fundamental research been done before. So it would be the same. I think all these studies would be helpful in future.
Greg?
Yeah, I think I'd agree with what Stephanie was saying, that And I think the expression "a rising tide floats all boats" is very true in science, and we're actually building up the capability, increasing capability of scientists within Europe, whether it's for a pandemic, but then that has an effect on other disciplines as well. And I think in other ways that, so I know a lot of engineers, even outside of the Eurofusion, that have been supporting that in the UK by actually developing or producing rapid prototypes of personal protective equipment for people in the health services. So it's not maybe supporting with a vaccine, but it's having the engineering capability to support in other ways as well. So that's something in Fusion we understand about protective equipment, something that we're quite versed in. So that's a way that we can support differently in the pandemic.
So we're about to end this session, but first, before that, I'd like to ask you a very last question to all of you, and I would like to bring back into focus the theme of this session, which is bringing the future closer to us. I would like to ask you briefly what you wish for yourself, for your group, for your field of research, for your organization, to do that, to bring the future closer. Let's say in the next decade. So let's go around the clock. So Isa, Stephanie, and then,
yeah,
and then Greg.
quickly. So I have only one point. I think right now, this pandemic is really explaining all of us that bringing both the public and the private sectors together, working together for a common cause. I think that's the how you can bring the future closer.
Stephanie?
Yeah, definitely. It's about collaboration and also willingness of politicians to invest in science in different fields, because it will bring us further, and not necessarily a vaccine, but it will increase our knowledge to handle whatever situation better, to understand better what is going on.
Elise?
I think in the same way as Stephanie and I would say that it's really important to continue to promote science, to do technological development to the extreme, as we have said in my presentation, because this is the only way to go to a sustainable world, to improve, as I said, the storage of hydrogen or all the discovery, and it's really essential to pursue the science development.
And Greg, you have the final words.
I think for me, the continued engagement and interest of both the public, politicians, but also industry as well. But maybe that's 3 wishes that I'm asking for, not just one there.
But that's good. Thank you very much. So just end up this session by thank you all, the 4 of you, for your presentation and your presence and your time on a Saturday evening. I wish you a very nice evening, and also to the audience, and hope to see you again very soon. Thank you very much to all of you.
Thank you.
Bye-bye.